Good morning to all of you. Welcome to the lecture on this Carnot cycle. Today, we are going to see this Carnot cycle, which is named after a scientist known as Carnot, who proposed it in 1824. This cycle represents the most efficient possible heat engine that operates between the two temperatures. It's not just a theoretical construction, it has a practical implication for how we understand and design real-world engines. In this lecture, we are going to study introduction to the Carnot cycle, what are the different processes in the Carnot cycle, the Carnot theorem, the efficiency formula of the Carnot cycle, the reversibility and entropy associated with the Carnot cycles, the limitations of the Carnot cycles, and the historical concept for the Carnot cycle. The Carnot cycle, as we all know, is an ideal thermodynamic cycle that consists of 4 reversible processes. Now, there are 2 isothermal processes and there are 2 adiabatic processes. It is named after the Carnot because he has proposed it. Okay, and the main purpose was to determine the efficiency of engine. So earlier there were the heat engines. So what is these heat engines? It is a device that converts heat into mechanical work. The efficiency of a heat engine is defined as the ratio of the work it produces to the heat input it receives. The Carnot cycle shows that there is a maximum possible efficiency for any heat engine operating between 2 specific temperatures, and no real engine can exceed this efficiency. The importance of the Carnot cycle can't be overstated. It provides a theoretical upper limit for the efficiency of heat engines, which is crucial for engineers designing the power plants, refrigerators, and other thermal systems. It also helps us to understand the second law of thermodynamics, which states that the heat cannot flow from a colder body to a hotter body without some form of work being done, and that some energy is always lost as a heat in any real process. In terms of relevance, the Carnot cycle is essential for understanding concepts like entropy, reversibility, and the direction of natural process. It's a fundamental tool in thermodynamics that has applications in physics, chemistry, engineering, and even in economics. To summarize, the Carnot cycle is an ideal model of a heat engine, most efficient possible heat engine between 2 temperatures, a key to understanding the second law of thermodynamics, a benchmark for evaluating the real-world engines. Before we move on the process, let's make sure that we understand some key terms. So first one is the isothermal process. It is a process in which temperature remains constant. Second is the adiabatic process, a process where no heat is exchanged with the surrounding. And third is the reversible process, a process that can be reversed without any change in entropy. The Carnot cycle is made up of this reversible process, which is why it is considered ideal. Also, it's important to note that the cycle operates between the 2 thermal reservoirs, a hot reservoir and a cold reservoir. The hot reservoir provides the heat to the system, and the cold reservoir absorbs the heat from the system. So, with this background, let's proceed to explore this process in detail. Now we will see the process in the Carnot cycle. The Carnot cycle consists of 4 key processes that together form a closed loop, allowing the system to return to its initial state. Each process plays a crucial role in the cycle's efficiency and operations. So let's go step by step. So first one is the isothermal expansion. In this process, the system is in contact with a hot reservoir at a high temperature, and this temperature is denoted as T high. The gas inside the system expands, and during this expansion, it absorbs heat from the hot reservoir, and this is denoted by Q input, that is Q in. The expansion is isothermal, meaning the temperature remains constant throughout the process. So, as the gas expands, it works on the surrounding. But the temperature doesn't change. It is continuously absorbing heat from the reservoir. Okay. Next is the adiabatic expansion. Now here, after the isothermal expansion, the system is thermally insulated, meaning no heat can enter or leave the system. So the gas continues to expand during this process and more work on the surrounding. Since there is no heat exchange, the expansion causes the temperature of the gas to decrease until it reaches the temperature of the cold reservoir. Third is the isothermal compression. Now, the system is brought into contact with a cold reservoir at a temperature T low. The gas is compressed by the surrounding doing work on it. As the gas is compressed, it loses heat to the cold reservoir, and this heat is denoted by Q out. Again, this process is isothermal, so the temperature remains low or constant, that is T low. Fourth is the adiabatic compression. The system is once more thermally insulated. The compression continues with the surrounding doing work on the gas. This work increases the temperature of the gas back to the T high, preparing it for the next cycles. Now, if you summarize the Carnot cycles, it involves absorbing heat at a high temperature during the isothermal expansion, expanding further without the heat exchange, cooling down to the low temperature, releasing heat at a low temperature during isothermal compression, compressing back to the initial state without heat exchange, heating to the high temperature. This sequence ensures that the cycle is reversible and achieves the maximum possible efficiency for the heat engine operating between the two temperatures. Now, let's make sure that we understand what each process means in terms of energy transfer. Now, in case of this isothermal expansion, the gas absorbs the heat which is generated by this Q in, and this the equal amount of Q in, since it is there is no internal change in an ideal gas at this constant temperature. Now, in the next process of the adiabatic gas expansion, the gas works on the surrounding and its internal energy also decreases, leading to the temperature drop. So in the next step, that is the isothermal compression, there is a work done on the gas, and it releases the heat output which is equal to the work. Okay. Now, since the work is done on the gas, increasing its internal energy and thus its temperature. So the net effect is that the system has converted some heat from the hot reservoir into the work, with some heat discarded to the cold reservoir. The efficiency of the cycle is determined by how much work is produced compared to the heat input, which will be we will discuss in the later slides. Now, for now, it's important to visualize this process. If you imagine a pressure volume PV diagram, the Carnot cycle forms a rectangular shape with two horizontal lines that are the isothermal process, and the two vertical lines are the curved lines that are the adiabatic process. Now here, in the summary, if you see, there is a isothermal expansion, there is a heat in, work out. Adiabatic expansion, there is a work out and a temperature down. Third is the isothermal compression, where the work is supplied and heat is taken out. And fourth is the adiabatic compression, where work is supplied and temperature has been increased. Now this completes the cycle, and the system is ready to repeat this process. Okay. Now we will see the Carnot theorem. The Carnot theorem is a fundamental principle in thermodynamics that has a significant impact for the efficiency of heat engines. Let's explore what is this theorem and why it is so important. First, what is a heat engine? is a device that converts heat into mechanical work. The efficiency of a heat engine is defined as the ratio of work it produces to the heat input it receives. So the efficiency is equal to work done divided by heat input. Now, the Carnot theorem states that no heat engine operating between the two heat reservoirs at a different temperatures can be more efficient than a Carnot engine operating between these same two temperatures. In other words, the Carnot cycle provides the maximum possible efficiency for any heat engine working between those two specific temperatures. Now, this theorem has two key implications. All reversible engines operating between the same two temperatures have the same efficiency. No irreversible engine can have an efficiency greater than that of a reversible engine operating between the same temperatures. So, what is a reversible engine? It is an engine that can be reversed in its operation without any loss or the gain of energy, meaning it can function as both a heat engine and a refrigerator or heat pump. The Carnot cycle is an example of a reversible cycle consisting of a two reversible isothermal process and two reversible adiabatic process. The efficiency of a Carnot engine is given by a formula. Efficiency is equal to 1 minus T cold divided by T hot, where T cold is the temperature of the cold reservoir and T hot is the temperature of hot reservoir. Now, this formula is very crucial because it shows that the efficiency depends only on the temperatures of the two reservoirs and not on the specific working substances or the design of the engines. Let me explain this formula with an example. Suppose we have a hot reservoir at 500 Kelvin and a cold reservoir at 300 Kelvin. The efficiency of a Carnot engine would be efficiency is equal to 1 minus 300 divided by 500, which gives 1 minus 0.6 is equal to 0.4 or the 40%. So the efficiency the engine can convert only 40% of the heat input into useful work, with the remaining 60% being discarded to the cold reservoirs. Now, an important point to note is that lowering the temperature of the cold reservoir has a greater effect on increasing the efficiency than raising the temperature of the hot reservoir. This is because efficiency formula involves ratio of Tc divided by Th. So decreasing the Tc or increasing the Th could increase the efficiency, but the percentage change is more sensitive to change in Tc when Tc is smaller as compared to Th, that is T hot. For instance, if we kept Th, that is hot reservoir at a constant temperature of 500 Kelvin and decrease the Tc, that is cold reservoir temperature from 300 to 250 Kelvin, the new efficiency is given by 1 minus 250 by 500 is equal to 1 minus 0.5 is equal to 50%. That's an increase from 40 to 50%, which is a 25% relative increase in the efficiency. On the other hand, if we keep T cold at a 300 Kelvin and increase Th from 500 to 600 Kelvin, the new efficiency is given by 1 minus 300 by 600 is equal to 1 minus 0.5 is equal to 50% efficiency. Again, an increase from 40 to 50% as the before. So in this case, both decreasing T cold by 50 degree Kelvin and increasing T hot by 100 degree Kelvin lead to the same efficiency or the same increase in the efficiency. However, in the absolute term, changing temperature of the cold reservoir has a more significant impact because it is in the numerator of the ratio. To illustrate that for a given change in the temperature, altering the cold reservoir temperature has a greater impact on the efficiency than altering the hot reservoir temperatures. This is because the efficiency formula is given by 1 minus T cold, that is the cold reservoir temperature divided by TH, that is the hot reservoir temperature. And the term Tc divided by Th is more sensitive to the change in Tc when Tc is smaller as compared to Th. So in practical terms, to maximize efficiency, it's more beneficial to minimize the temperature of the cold reservoir than to maximize the temperature of the hot reservoir. However, there are practical limits to how to lower the cold reservoir temperatures. For example, in power plant, the cold reservoir is often the environment, like the river or the atmosphere. And so this cold reservoir temperature is fixed. On the other hand, TH, that is the hot reservoir temperature, can be increased by using high temperature heat source. But there are material and economic constraints. Another important aspect of the Carnot theorem is that it establishes a standard for comparing the performance of real heat engines. Since no real engine can achieve the Carnot efficiency, the difference between the actual efficiency and the Carnot efficiency indicates the extent of irreversibility in the engines. Therefore, in summary, Carnot theorem tells us that the Carnot cycle sets the upper limit for the heat engine efficiency, and all real engines will have the efficiency less than or equal to this limit, with equality only if the engine is reversible, which is not possible in practice. Therefore, the key points for this Carnot theorem is that it states that no heat engine can be more efficient than a Carnot engine operating between the same temperature. The efficiency of the Carnot engine is given by 1 minus Tc divided by T0. Lowering the cold reservoir temperature has a greater impact on increasing the efficiency than rising the T hot for the same, that is the hot water reservoir for the same temperature change. The Carnot theorem provides a benchmark for evaluating the performance of real heat engines. Now we will see the formula of the efficiency of the Carnot cycle. The efficiency of the Carnot cycle is very crucial concept in thermodynamics because it represents the maximum possible efficiency that any heat engine can achieve when operating between the two given temperatures. This means that no real heat engine can be more efficient than a Carnot engine working between the same hot and cold reservoirs. First, let's recall what efficiency means in the context of a heat engine. Efficiency is defined as the ratio of useful work output to the heat input. So here it is given by W divided by QH, where W is the work done and QH is the heat input. In Carnot cycle, the work done by the engine is equal to the heat input minus the heat output. Therefore, W is equal to QH minus QC. Okay. Now here, the efficiency formula can be written as W, which is equal to QH minus QC divided by QH. So it becomes 1 minus QC divided by QH. Now, for a Carnot engine, the heat input and the heat output are related to the temperature of the hot and the cold reservoirs. Specifically, in the reversible process of the Carnot cycle, the ratio of heat transfer to the work done is determined by the temperatures. From the first law of thermodynamics and the properties of reversible process, it can be shown that QC by QH is equal to TC by TH, where TH is the temperature of the hot reservoir and TC is the temperature of cold reservoirs, and both these temperatures are in Kelvin. Substituting this in the ratio, the efficiency formula is given by 1 minus Tc by T hot. And this is the fundamental formula for the efficiency of the Carnot theorem. Okay. Now here, as we have discussed, the efficiency depends upon the temperature of these two reservoirs. Okay. And this reservoir temperatures, we have also seen what is their impact. So we can see it was important that the temperature of the cold reservoir is important as compared to the hot reservoirs. Okay, because if the cold reservoir temperature we are decreasing, we are getting more we can say output in the efficiency. Okay, so now in the next session we will look upon the reversibility and entropy. Now we will see this concept, okay, which is continued of this entropy and reversibility. Now here in the Carnot cycle, since it is a reversible, the entropy change of the system for each process can be calculated, and the net entropy change over the time is zero, as we have seen in the previous slide. Now let's look at each process one by one. First, if we consider the isothermal expansion, the system absorbs some heat, that is QH, from the hot reservoir at a temperature TH. The entropy change of the system is given by delta S is equal to QH divided by TH. The entropy change of the hot reservoir is given by delta S hot is equal to QH by TH. Now here, the total entropy change is given by delta S is equal to delta S system plus delta S hot, that is equal to 0. Now in case of this adiabatic expansion, since there is no exchange of heat, so Q is equal to 0, therefore delta system is equal to 0. And the surrounding have no entropy change. Therefore, delta S total is equal to 0. Now, in case of this isothermal compression, the system releases heat QC to the cold reservoir, which is maintained at temperature TC. The entropy change of the system is delta S is equal to QC by TC. And the entropy change of the cold reservoir is delta S cold is equal to QC by TC. Therefore, delta S total becomes delta S system plus delta S cold, that it becomes equal to 0. Now, in case of this adiabatic compression, means no heat is exchanged, so delta S is equal to 0. So that the surrounding, we can have no entropy change. So delta S total is equal to 0. Therefore, for the entire cycle, the total entropy change is 0, which is consistent with the reversibility of the process. Now, in the rear heat engine process are not reversible. There are always some irreversible steps such as friction or the heat transfer across a finite temperature difference, which leads to an increase in the entropy. This means that for the real engine, the total entropy change for the cycle is greater than 0, indicating that some energy has been dissipated as heat, reducing the engine's efficiency. The Carnot cycle, being reversible, has no such dissipation, hence its efficiency is the maximum possible. Another way to look at the entropy is through the concept of entropy production. In reversible process, entropy is not produced, it's only transferred. In irreversible process, the entropy is produced within the system. So the Carnot cycle efficiency is tied to its ability to operate without producing any entropy, which is why the most efficient cycle possible. To illustrate this, consider that the efficiency of a heat engine can also be related to the entropy change. The work done by the engine is QH minus QC. From the entropy perspective, QH is equal to TH into delta S. Okay, we are modifying this formula and putting in this. But the Carnot cycle, delta S for the system QH by TH and delta S cold for the system is minus QC by TC. So this cycle is the closed cycle. The net entropy change of the system is equal to delta S hot is equal to delta S cold. Therefore, QH by TH is equal to QC by TC, leading again to efficiency formula, which is given by 1 minus TC by TH. So in the real engines, because there are certain irreversibilities, QC by QH is always greater than TC by TH, which means that more heat is discarded to the cold reservoir than in the Carnot cycle, reducing its efficiency. In the summary, its Carnot cycle's reversibility ensures that the entropy is conserved, leading to the highest possible efficiency. Understanding the entropy and irreversibility is essential for grasping the fundamental limits of the heat engine's performance. Now, we will see certain limitations of the Carnot cycle. The Carnot cycle is an idealized model that provides the maximum possible efficiency for a heat engine operating between two temperatures. However, it's important to understand that this cycle has limitations, and real-world engines cannot achieve this efficiency Now let's explore what is that. First, the Carnot cycle assumes that all processes are reversible. In reality, no process is perfectly reversible because there are always some dissipative effects such as friction, heat transfer across finite temperature differences, and other sources of energy loss. For example, in a real heat engine like a gasoline engine, there is a friction between moving parts, heat is lost to the environment, and the combustion is not instantaneous or perfectly controlled. These factors make the engine operation irreversible, leading to lower efficiency compared to the Carnot cycle. Second, the Carnot cycle requires that the heat transfer occurs at a constant temperature, which means that the working substance must be in thermal equilibrium with the reservoir during the isothermal process. In practice, achieving the perfect thermal equilibrium is impossible because it would require infinite time for the heat transfer. In real engines, heat transfer happens over a finite temperature difference, which is an irreversible process and results in entropy production, reducing the engine efficiency. Third, the Carnot cycle involves ideal gases or other idealized working substances that do not exist in reality. Real working substances have properties that deviate from the ideal behavior, such as the real gases have van der Waals forces and they may undergo phase change or may have other complexities. These deviations from the ideal behavior can affect the performance of the engine and makes it less efficient than the Carnot cycle. Fourth, the practical constraint in design and operation also limits to the efficiency. For instance, in a power plant, the choice of the material limits the maximum efficiency that can be used for the hot reservoir. Higher temperatures might lead to better Carnot efficiency. But if the materials cannot withstand those temperatures, the hot reservoir temperature must be lower, reducing the efficiency. Additionally, economic considerations play a vital role. While increasing the efficiency might require more complex and expensive designs, there is a trade-off between the cost and efficiency that must be balanced in the real-world applications. Despite these limitations, the Carnot cycle is extremely valuable because it provides a theoretical upper limit for the heat engine efficiency. This allows engineers to evaluate how close their designs to the ideal and to identify the areas for the improvements. Therefore, the limitations of the Carnot cycle are first, it assumes the reversibility, which is not achievable in practice. It requires the ideal conditions that do not exist in the real engines. Third is the practical constraints in the material and the design further reduces achievable efficiency. However, understanding these limitations helps us to appreciate the importance of minimizing the irreversibilities and optimizing the heat engine designs to approach the Carnot efficiency as closely as possible. Now let's look at the certain historical context which is related with the Carnot cycle. As you all know, it was proposed by Mr. Sadi Carnot in 1824, okay, which was detailed in his work such as Reflections on the Motive Power of Fire. At the first time, steam engines were the central to the industrial revolutions, and the Carnot aimed to maximize their efficiency. His cycle introduced the concept of reversible heat engines, demonstrating that efficiency depends solely on the temperature of cold and the hot reservoirs. This idea was revolutionary, laying the foundation for the second law of thermodynamics, which states that the heat cannot flow from the cold to hot body without work. Although Carnot work was not widely recognized during his lifetime, it was rediscovered in 1840s and 50s by the scientists like William Thomson, also known as Lord Kelvin, and Rudolf Clausius, who formalized the second law based on his insight. His historical developments influenced modern thermodynamics and engine designs, making Carnot's contribution fundamentals. Now, looking to this modern relevance of these Carnot cycles, in contemporary times, the Carnot cycle remains a cornerstone for the thermodynamics and engineering. It provides the theoretical upper limit for the heat engine efficiency calculated by 1 minus Tc by T naught. Okay. Engineers use these limits to evaluate and improve the efficiency of real-world heat engines such as internal combustion engines, steam turbines, and gas turbines. For example, the power plant, the difference between the actual efficiency and the Carnot efficiency highlights the potential improvements. The cycle also has an important significant on environmental implications, aiding in assessing energy system efficiency to reduce the carbon emissions, crucial for sustainability. Research into advanced materials like high temperature alloys aims to minimize the losses and approach the Carnot efficiency, impacting the fields like renewable energy. Solar thermal power plants, for instance, use the concentrated solar power to heat the fluids, and their efficiency is benchmarked against the Carnot limit to optimize the electricity generations. Additionally, the cycle applies to the refrigeration and the heat pump systems also, where it helps to evaluate the cooling efficiency. Understanding the Carnot cycle also informs energy policies, encouraging investments in efficient technologies to address the climate change challenges, ensuring the future generations are equipped to tackle the energy related issues.